Unit 8.1 is similarity in right triangles. Similarity in right triangles. Now, when we're thinking similarity, we're thinking same shape, corresponding angles are equal, corresponding sides are in proportion, so we're thinking proportions. Now, it says find the geometric mean. To find the geometric mean between two numbers, you multiply them and take the square root. Now, let me show you what geometric mean actually is. The geometric mean between 4 and 9 would be properly written as a proportion as 4 over 9, 4 over x equal x over 9. If x is the geometric mean between 4 and 9, then 4 over x equal x over 9. To solve, you would cross multiply see, cross multiply, you get the product of them. And then you're going to get rid of the square with the square root. And so what you end up doing is multiplying them and taking the square root. So we could set it up in a proportion. If we want the geometric mean between 4 and 9, we could say 4 over x equal x over 9. Cross multiply. But when we do, we're going to end up with the square root of the product. Multiply and take the square root. So what I just have people do is just memorize. If you want the geometric mean between 4 and 9, you take the square root of the product of 4 and 9. The product of 4 and 9 is 36, and the square root of 36 is 6. The geometric mean between 5 and 9 is the square root of the product of 5 and 9. Now, the square root of 9 part of this has a perfect square 3. So out would pop its perfect square root, and the little 5 would stay in 3 square root 5. You may say, well, I didn't like that. I don't know what you just did. Well, let's just go and multiply them then. 5 times 9 is 45. Divided by 3 is 15. Divided by 3 is 5. Rewrite it as the product of its primes. Circle sets of 2 for square root. There's your 9. From each set, you bring one out. There's your 3. What didn't get circled in a set goes back in. There's your 5. 3 square root 5. Any questions on finding the geometric mean? So to find the geometric mean between two numbers, you can say first number over x equal x over second number and cross multiply, or you can just get right to it, multiply and take the square root. Now, if the altitude is drawn to the hypotenuse of a right triangle, then if the altitude is drawn to the hypotenuse of a right triangle, then the altitude is the geometric mean. Multiply and take the square root. The altitude is the geometric mean between the two segments of the hypotenuse, or the two pieces of the hypotenuse, and either leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to that leg. In other words, hypotenuse and the piece closest to it, adjacent to, closest to, next to. So The altitude, here's the given, here's the if the altitude is drawn to the hypotenuse of a right triangle. You got to start out with a right triangle. In a right triangle, the side opposite the right angle is called the hypotenuse. So here's the hypotenuse. An altitude is from a vertex perpendicular to the line that contains the opposite side. So in red there we have the altitude drawn to the hypotenuse of a right triangle. If the altitude is drawn to the hypotenuse of a right triangle, then the altitude is the geometric mean between the two pieces of the hypotenuse and either leg is the geometric mean between the whole hypotenuse, which is 13, and the segment of the hypotenuse adjacent to that leg. So this leg is a geometric mean between the hypotenuse and the segment of the hypotenuse closest to it. This other leg, Z, is a geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to it, or closest to it. Now, the way I let people help them learn this is if you draw a little circle, you've got all three pieces that go together. The altitude is a geometric mean between the two pieces of the hypotenuse. You see that that little blue circle hits all three of those? The altitude is the geometric mean between the two pieces of the hypotenuse. And I'm going to make little arrows. This leg, Y, is a geometric mean between the hypotenuse and the piece of the hypotenuse adjacent to it. So that little arrow tells that story. This leg, Z, is the geometric mean between the hypotenuse 13 and the piece of the hypotenuse closest to it. So again, altitude is geometric mean between two pieces of hypotenuse. Either leg is a geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to that leg. The little blue circle hits the altitude in the two pieces. Altitude is geometric mean between two pieces. This little green hits this leg, the piece closest to that leg, and hypotenuse. This leg is the geometric mean between the hypotenuse and the piece closest to it. This arrow hits three things. It hits that leg, this piece of the hypotenuse, this piece of the hypotenuse and the whole hypotenuse. So this leg Z is a geometric mean between the hypotenuse and the piece of the hypotenuse closest to it. Okay? So the altitude X is the geometric mean between the two pieces of the hypotenuse 4 and 9. So X is equal to the square root of 36, which is 6. This leg Y is a geometric mean between the hypotenuse 13 and the piece of the hypotenuse 4 closest to it. The square root of 4 is 2, so we're going to get 2 square root 13 simplified. This leg Z is a geometric mean between the hypotenuse 13 and the piece of the hypotenuse 9 closest to it. Square root 9 is 3, so out pops a 3, square root 13. Okay? Any questions on that? Naming the similarity. Let's look at how to name the similarity. If the altitude is drawn to the hypotenuse of a right triangle, then all three triangles are similar, and using the proportions that come out of the similarity is where that little corollary came from. Those proportions would be that proportion looking geometric mean thing, 4 over x equal x over 9, that. So using the similarity proportions would give us those geometric mean proportions, which would then create these little formulas, okay? Now, we want to name the similarity, and we're trying to name the whole big triangle. Similar to this little triangle on the left, similar to this little triangle on the right. And when we name similarity, we have to line up all of our corresponding parts. So we got to really think through this. Now, the easiest thing to know that in the right triangle, in the whole big right triangle, B was the right angle. In the little one on the left, D was the right angle. B was in the middle, so D is going to go in the middle. The right angles are the easiest ones to find, so I'm going to put D in the middle here and D in the middle here. Now we got to think a little bit. You see how that one's pointier than that one? In other words, this one's smaller. In the whole big triangle, which of the two non-right angles was smallest? Well, in the whole big triangle, C was the smallest, right? In the little triangle on the left, that little b is the smallest. So little b of the one on the left goes with C of the whole big thing. C of the whole big thing was last, so the b of the one on the left goes last, and so I'm going to put the b there. And so the smallest of the one on the right would go last, which is C of the acute angles. The medium size acute angle, or the medium size angle here, is A. It would go with the medium size angle of the one on the right, B. And it would go with the medium sized one of the one on the left, A. So A of the triangle on the left is obviously the same angle as the big one. So A of the big one and A of the small left are equal because they're both A. Notice that C of the big one and C of the small one on the right are the same angle C, so they went together. So we named that similarity. Let's see how we got that. Okay? All right. So here's an example. Let's look at the daily work unit 8.1. Let's just do number 4. Number 4, we want the geometric mean between 7 and 12. We could set up a proportion, 7 over x equal x over 12, and cross multiply. Or we could just skip that and go right to the little shortcut we learned. The geometric mean is the square root of the product. Now we would get the square root of 84. But the 84 will break down. Let's look at it. 84 divided by 2 is 42. Divided by 2 is 21. Divided by 3 is 7. We would rewrite it as the product of its primes. 2 times 2 times 3 times 7. We've got a pair of 2's. We make a new radical. from the set of 2's, we bring out A2. These non-circled go back in. If there's more than one outside, you multiply. If there's more than one inside, you multiply. And so we get 2 square root 21. Okay? Any questions on that? All right, we'll just look at number 5. Number 5, we want to name the similarity. We've got AXP as the big one. Now, easiest way to go, angle A of the big one and angle A of the small left are the same angle. You see that? Angle P of the big one and angle P of the small right one are the same angle. P was last, P was last. X of the big one is the right angle. On the little ones, E was the right angle both times. So we're going to put E in the middle, E in the middle. If you do it like this, then it's a little easier than what I showed you a while ago. What I was showing you a while ago is trying to match up each one. And then at the end of all of that, we were saying, okay, notice that A of the one on the left is the same as A of the whole thing. And notice that the P here of the one on the right is the same as the whole thing, except then it was A and C. So if we get that common angle first, see the red A, and that common angle on the right, that blue P, and then we get our right angles next, then on the one on the left, we just have to find the other letter. A, E, what? Well, X. See? Well, the one on the right, it's just whatever's left. E, P, what's left? X, you see. And so we named the similarity. But so we did that. We got the common angles, and then we got the right angles, and then we got the leftover angles. I want to back up and show you that. It's going to say that here. See, the 90-degree angles, we got the right angles. We got the common angles, and we got the leftover angles, okay? Let's look at 7, 8, and 9. 7, 8, and 9. If the altitude see, we got to make sure the if is true, is drawn to the hypotenuse of a right triangle, then, well, we can reach a conclusion because I gave you the if part of a theorem. If the altitude is drawn to the hypotenuse of a right triangle, then the altitude x is the geometric mean between the two pieces of the hypotenuse. Altitude x is equal to the square root of piece times piece. And either leg is the geometric mean between the hypotenuse and the piece of the hypotenuse adjacent to that leg. So y is equal to the square root of hypotenuse 11 times piece closest to it 3. This leg z is the geometric mean between the hypotenuse 11 and the piece closest to it 8. Okay? So we're going to get x is equal to square root 24. If you can mentally think square root 4 times square root 6 and square root 4 is 2 and get 2 square root 6, then that's fast. If you have to break it down, that's fine. Pair of 2's. Pop out a 2, in goes the 6. 2 square root 6, any way you go at it, for x. The altitude is the geometric mean between the two segments of the hypotenuse, or altitude is equal to the square root of piece times piece. Square root 11 times square root 3 is square root 33, which will not break down. Leg y is the geometric mean between the hypotenuse and the segment of the hypotenuse closest to that leg, or leg equals square root of hypotenuse times closest piece. The other leg z is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to that leg. In other words, leg z is equal to square root of hypotenuse times piece closest to it, 8. So we get square root 88. We'll break that down. 88, divide 2, 44, divide 2, 22, divide 2, 11. 11 is prime, so we have square root 2 times 2 times 2 times 11. We got a pair of 2's. We make a new radical. From the set, out pops a 2. What didn't get circled in a set goes back in. You multiply 2 square root 22 simplified. So if the altitude is drawn to the hypotenuse of a right triangle, then the altitude is the geometric mean between the two segments of the hypotenuse, and either leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to that leg. In other words, altitude is equal to the square root of piece times piece. Altitude is equal to the square root of piece times piece. Leg is equal to the square root of hypotenuse times closest piece. Leg equals square root of hypotenuse times closest piece. Other leg equal to the square root of hypotenuse times closest piece. Leg is equal to the square root of hypotenuse times closest piece. If you'll say the rules as you use them, then you can commit those rules to memory long term. Okay? And I gave you lots of these to practice, which you need lots to practice on. Let's look at let's look at the last set there. Here I gave you the legs and I didn't give you the pieces. So this gets a little more complicated when I don't give you the pieces of the hypotenuse. So let's just look at that particular problem and let's try to set it all up. So we're going to use our little deal. We have the altitude drawn to the hypotenuse of a right triangle. So we say altitude x is equal to the square root of piece times piece. X is equal to the square root of y times z. X equal, I want to move it over here. X is equal to the square root of piece times piece, y times z, which is yz. Well, we can't do a whole lot with that, can we? Either leg is the geometric mean between the hypotenuse and the piece of the hypotenuse adjacent to that leg. So that leg 8 is equal to the square root of hypotenuse 4 square root 13, and that piece closest to it, y. So 8 is equal to the square root of 4 square root of 13 times y. The other leg, 12, is a geometric mean between the hypotenuse and the piece of the hypotenuse closest to it. In other words, this leg 12 is equal to the square root of hypotenuse 4 square root of 13 times the closest piece z. So 4 square root 13z. Now we can't solve the blue because there's 3 variables. We can solve the green, there's only 1 variable. To get rid of the square root, we would square it. And so we would have, that's not a very good looking square. Let me try to do a better job there. To get rid of the square root, we would square it. So we would have 8 squared is 64 is equal to 4 square root 13y. Well, now we're going to undo multiplication by division. So we're going to have 4 square root 13, 4 square root 13. And this is where all that simplifying radical stuff becomes handy, necessary. I'm going to go the other way with this. Y equal. Now 64 divide 4 is 16. So that's going to be 16 square root 13. Okay? I'm sorry. It's going to be 16 on top, square root 13 on bottom. 16 over square root 13. 4 goes into 64 16 times. But you can't have a radical in the denominator, so we rationalize the denominator by multiplying by square root 13, and we get 16 square root 13 over 13 for y. Now, we could say the whole thing, 4 square root 13 minus 6 square root 13 over 13, right? The whole hypotenuse, 4 square root 13, minus y, that little piece on the left, 16 square root 13 over 13. And we can subtract. But to subtract, we need a common denominator, so we're going to leave this 16 square root 13 over 13. We're thinking 4 over 1 is how many 13ths? So you'd multiply by 13, and you'd have 4 times 13 is 52. So that 4 is the same as 52 13ths. So we have 52 square root 13 over 13ths. In other words, the 52 13ths part gives you the 4, and then you have still have square root 13. So now you can subtract 52 of those minus 16 of those would leave 36 of those little square root 13ths over the common denominator, 13. And so the z would be, I'm double checking my work here. This is kind of fun answers. Okay. I was correct. I just wanted to double check my work so I didn't lead you astray. And so this is 36 square root of 13 over 13 for z. And now we have x. Now we have y and z, and so we could solve for x. So x is equal to the square root of y times z. Y is 16 square roots of 13 over 13. And z is 36 square roots of 13 over 13. Now, I know this is a lot of stuff, but what times itself is 16? That's under a square root, 4. What times itself is 36? 6. We have a pair of square root 13s. And we want what times itself, so we have that twice, so we pull 1 out. We have 13 twice on bottom, so we pull 1 out. So from the 16, we pull out what would have been a pair of 4s. From that pair of 4s, we'd pull out a 4. That 36 is really a pair of 6s, so we pull out a 6. We have a pair of square root 13s on top, so we pull out a square root 13 on top. We have a pair of 13s on bottom, so we pull out a 13 on bottom. And so we're going to get 4 times 6 is 24 square roots of 13 over 13 for x, 24 square roots of 13 over 13. Thought I'd go ahead and do this one for you uh, since we're dealing with some radical stuff here. This is a little bit of a complex problem, but we did want you to have some experience with radicals. We don't want you to be scared of doing fractions and decimals and radicals because those are real numbers that you have to deal with in algebra 2 and college algebra and etc. So on. So don't skip these problems. Learn how to deal with them. Go ahead and endure the pain and get it done and learn it. Okay. So we have some more problems to practice naming the similarities, and then we have some discovery work for the Pythagorean theorem. That discovery work would lead into Unit 8 2 Pythagorean theorem. So that's all of the 8-1 homework, and